Okay, let's look at our new section on linear transformations, where hopefully we'll take some of the stuff we've been doing and make it a little bit more concrete while also making it a little more formal. So the first is a couple of definitions. A transformation is a function that takes us from Rn to Rm, right? So in other words, it assigns each vector x that's in Rn to a vector tx in Rm, or t of x. Right, so just the same sort of function notation, right, where t of x is a vector that lives in this space. The domain is the set of all possible input vectors x, right? So in this case, Rn is our domain, right? So the space where all of our x's are coming from. The output tx, or t of x rather, is called the image of x under t. Right, so you might have heard that used in function notation, but the image is just going to be the output that we get. Whereas the range is the set of all of our images. Right, so if I have, say, some output here, so for every x that I get, I apply the transformation to it. All of those outcomes make up my range. The codomain is different, right? So the codomain is the vector space that contains the range of t. So, right, so my codomain here is Rm, which might or might not be the same thing as my range. Right, so the idea is that if I've got this point is denoting some vector that lives in Rn, the t transforms it, taking it to Rm, to this other vector t of x, and then that's, right, all the places that I could go would make up my range. Right, so a nice little example. So if I think about my transformation from R to R is x squared, right? So obviously my inputs are real numbers, so that's R. The place where my outputs live are one-dimensional real numbers, so that's also R, right? That's my codomain. But I'm never going to get negative numbers when I apply this transformation, right? So if I look at all the outputs that I'm ever going to get, I'm never going to get -1 or -2 and so on. So my range is only numbers that are greater than or equal to 0. So that's an example where your range could be different than your codomain. Okay, so let's talk about linear transformations. A transformation is linear if, for any u and v in Rn and any scalars c and d, 1, t of u plus v is equal to t of u plus t of v. 2, t of cu is equal to c times t of u. Right, so these two things basically are what we need to show that a transformation is linear, right? Like, so by definition, if these hold, the transformation is linear. If it's linear, then these two things will happen, right? So the combined definition, it's a little more succinct, but a little bit more challenging to prove or disprove sometimes, is t of cu plus dv, right, is equal to c times t of u plus d times t of v. Right? So in other words, it's just kind of combining these two steps. And if you think about it, it's like, can I take this vector and rewrite it as a linear combination in some sense? And if you can, well, that's how we got linear combination. That's how we're thinking of linear transformations. So for example, is t from R2 to R2, right? So if I've got t of xy is equal to x plus y and 2y, is that linear? Well, let's look at, get rid of some of that work so it's not too much. So t of x1 plus x2, y1 plus y2. Right, so it's kind of like I've got two vectors now instead of just a generic xy. I've got the vector like x1, y1 and the vector x2, y2. And so I'm doing this part 1 up here. What happens if I add the two vectors together? Well then, on top, the rule would be, right, this plus this, right? And then below I'm multiplying it by 2. Well, kind of because of associativity and commutativity, I can get this pretty quickly, right? So I've got x1 plus y1 plus x2 plus y2, 2y1 plus 2y2, right? And so I skipped a little bit here, but you can kind of think, right, if I'm doing this, that's like I'm adding these, and that would be t of x1 y1 plus t of x2 y2. So this is, as far as this is concerned, so far it's linear. What we'd still have to do, and good practice on your own, pretty easy, is show that t of c times xy is equal to c times t of xy. Right, so these two together will show that this transformation is linear. Notice that whenever I was showing this was linear, I had to use general variables. Like, it's not sufficient if I just said, let me check at 2, 2 and 2, 3, and it works, right? So you've shown that it works for 2 points out of infinite, and that's not going to be sufficient. However, what's nice, so is this linear? What's nice is that if we want to show something's not linear, we only have to show one point where it breaks. So there's a couple of things we could do here. What I'm going to do is, right, so if I say t of 2, 2, right, well that's going to be 2 times 2 over 2 plus 4, which is 4, 6. Now, think about, right, so this is 2, 2, so t of 1, 1 is going to equal 1 times 1 over 1 plus 4, right, which is 1, 5. Now, 2 times 1, 5 is definitely not 4, 6, right, so this is kind of the heart of what we're showing, right, so this is what it means when we say up here that this, where was I, right, that t of cu is equal to c times t of u, right? Like these two things should be the same and they're not here. Essentially, you can kind of think about all the things that we traditionally think aren't linear are going to be highlights that you're really trying to disprove if something's linear. Right, so if I saw like sine of x or sine of y, I'm going to think, well, that's not linear, right? The only thing that you really want to kind of be careful for that we don't expect often, kind of using that intuition, is that, right, adding something like this, and we might be more used to that from our tasks in class, but y plus 4 makes this thing not linear just as much as xy does, right? Straight adding by constants is not going to give us a linear transformation. So counterintuitive, but we can kind of saw why in some of our problems. Essentially, it's because things won't stick around at 0. Okay, so let's move on to matrix transformations. So we've kind of already worked with these, and now let's go back and talk about what they are. So if A is an m by n matrix, then the matrix, transformation, right, T sub A from Rm to Rn is given, right, T of x is equal to A times x. Right, so I kind of had us do that without really formally saying that's what was going on. So let's say that we write T going from R2 to R3 as a matrix transformation. Right, so my transformation here is just saying, right, x1, x2, and this is just another way of, right, like x1, x2, well that's ugly, but, right, this is vector. Then, right, x1 minus 2x2, x1 plus x2, x2 minus x1. Right, so can I write this as a matrix transformation? And in order to do that, right, I can kind of, just like if I was doing parametric vector form or thinking about solutions, I'm going to get my columns of x1s, my columns of x2s. So I had to do a little bit of switching here. And so this ends up, the coefficients give me my vector, so 1, 1, negative 1, right? And my x2, negative 2, 1, 1. Right? And so, right, this is just matrix multiplication, right? Like this is the linear combination that corresponds with this matrix times x1, x2. So it is a matrix transformation, and in fact, this is the matrix of transformation. And so thinking about A, right, as our matrix, like so this matrix, meaning right, A times X, you can, I think, see even easier if we're getting used to the idea of thinking about how vectors correspond with matrices. You might be able to see this even easier. What the domain is, right? So the domain is going to be the number of columns in my matrix. You can think about that because the number of columns in my matrix is going to correspond with the number of entries in my input vector, right? So I started with R2, right? And then you can see that here, and that shows up in my number of columns, right? The number of rows is the dimension of my output, right? So that's my codomain. So, right, 3 entries, right? So my vector is going to have 3 entries. You can kind of see those here. It's going to be a linear combination of these two. And my codomain is R3. You can kind of see, hopefully we're comfortable enough now with the idea of span that you can sort of see that the range is not going to be all of R3. Right, because all of our answers, like you can kind of see here, all of our answers are going to be a linear combination of these two vectors, right? So x1 and x2 can be anything, so all possible linear combinations of these are going to be the range. Notice that I'm not going to span R3 if I only have 2 vectors in R3. Okay, so if I say something like find the image, right? So find the image TU, if I give you that U is 1, 5, well, essentially this is just a very basic multiplication problem, right? So U is 1, 5, that goes here, and then I perform the calculation, right? So that's just saying, right, A times 1, 5, so do the linear combination, and I just did that in my head as I was writing it up real quick, so hopefully I didn't mess up adding, but it should be negative 9, 6, and 4. Right, so that's going to be the image vector T of 1, 5. Okay, and then the last thing I want to say is, so for practice for this material, you'd want to be able to find T of V if V is equal to negative 3, 3. So literally what I'm going to have us do for the iClicker quiz, or at least one of the questions on Tuesday, is find T of V for this exact vector V and this exact transformation matrix. Okay, so that's all I have for now. I actually have a little bit more I want to cover, but this is all we need for Tuesday, and I wanted to get it out before it got away from me. Have a nice rest of your weekend. I will see you Tuesday.